All right, welcome back to Meteorology 101. Visit my website, meteorology101.com. And if you haven't already, subscribe to my channel. So, in this video, I'm going to kick off a new series. We're going to start with a whole new series on weather analysis and forecasting. So, when the course is finished, these are the subjects we're going to be covering is physics, observations, thermodynamics, upper air analysis, surface analysis, weather systems, satellite, radar, convective weather, and prognosis. So we're going to start off with physics. I got that prepared now. It's probably going to take a few videos. I don't want to go 2-3 hours on a video just to cover physics in one hit. So I may do a complete recording and then just break it up into sections so it's bearable. Physics is one of the toughest parts in weather, but we don't get into all the equations for a reason coming up. So just in physics alone, we're going to cover math, time, distance, direction, and velocity, mass, force, and pressure, temperature, density, water, Coriolis force, wind forces, geostrophic wind, gradient wind, cyclostrophic wind, vorticity, horizontal coordinate systems, vertical coordinate systems, scale, atmospheric structure, and global circulation. So then we'll get into a little bit more after that. If you look at the list here, next would be observation. So right now we're concentrating on physics. We're going to cover all these topics in physics. So like I said, this might take a few videos to complete. All right, in math and meteorology is used for the understanding of how weather works. By the time you solve the equation or determine weather parameter, the atmosphere has changed and you have to start over. That is atmospheric dynamics. Dynamic means changing. The atmosphere is constantly changing. So by the time you figure this stuff out, it's too late. So we let the computers do this. We just need to touch base on the physics, on the math of this thing to understand how these forces work together. Like right here is density, mass, and volume. Directly proportional and inversely proportional. So if two objects, substances, I guess, are directly proportional. So if density equals mass over volume, with volume held constant, if mass is increased, density will increase. And again, with volume held constant, if mass decreases, density will decrease. Inversely proportional is the density and the volume. So if you hold mass constant, you increase the volume, then that density will decrease. If you decrease the volume, now you're packing all that mass into a smaller area. Now the density will increase. So that's directly proportional or inversely proportional. The fundamental quantities, almost all atmospheric field variables can be defined as combinations of the following fundamental quantities: mass, length, and time. So mass is the amount of matter in an object, length is the measure of distance, and time is a period over which an action takes place. So fundamental units. The fundamental units give a standard against which fundamental quantities can be measured. So mass is measured in kilograms, length in meters, and with weather you'll also see kilometers, and then time is a fundamental unit. Time is second. All right, so the significant digits of weather, what you will see as you're looking at different charts, SCUTs, weather charts, upper air charts, surface charts, you'll see these significant digits. So wind speeds are 5 knots. So if we look at a surface chart, we can see that every 5 knots is plotted on a surface chart, even though it could be 3 to 7 knots. That would be indicated as a 5-knot wind because it's rounded to the 5 knots. Okay, so winds on surface knots are whole knots. They don't ever go 5.5, 4.5, anything like that. It's always the whole knot. And then pressure on upper air plots is the whole millibar. Pressure on a surface plot is 1/10. So we'll take a look at this in a minute. I'll pull up a surface chart. Temperatures on a SCUT chart is 1/10 of a degree. All other temperature are whole degrees. And relative humidity is a whole percent. heights on a upper air plots are decameters. Okay, time. Measurement is in the second. Weather systems flow across time zones. So meteorologists use Universal Coordinated Time, UTC, also known as Greenwich Mean Time, GMT, or Zulu. Typically, if you hear me talking about time, it's going to be in Zulu. So I'll say 1500 Z, something like that. That's pretty much easier to say, easier to remember, and it all means the same thing anyway. UTC ignores daylight saving time, so the example is like I'm on the East Coast, Eastern Standard Time is converted by adding 5 hours or 4 hours when Eastern Daylight Time is in effect. So right now we are 5 hours difference, so we will add 5 hours to our local time to get the UTC or Zulu time. Distance, direction, and velocity. Distance is a measurement of space separating 2 points. So from point A to point B, that's the distance. Often expressed in kilometers. Two-dimensional extent is area, measured in square meters. Three-dimensional extent of volume is measured in cubic meters. Direction describes where the wind is coming from, expressed in degrees relative to northeast, south, and west. Velocity is the distance covered in a specific time and has magnitude, speed, and direction. And gravity is 9.8 meters per second. So the first second, the object is unaffected by air resistance and is traveling 9.8 meters per second after the first second, and then 19.6 meters per second after the second second. All right, so I'm going to go back a slide. We're going to look at a surface chart real quick. So let's go pull up a surface chart, and we look at these. Let's look at the surface plots. Plot the station plots on this chart. We'll go through just some of the readings here. There's a lot more to these surface plots that you won't see on these charts. For symbols, cloud symbols, pressure rising, decreasing, a lot of that stuff. So right now we got like this station. Let me get my draw pad up here. Okay, so right there, station pressure. Remember we said that's into the tenths. So you'll see 1,014.2 millibars. Okay, at that station. Wind is in 5 knots in the whole knot. So this one, that's a 10 knot wind. This would be a 5 knot wind right there, 5 knot wind right there. So you got the wind barb, and then you got the little flag off to the side. That's a 5 knot wind. So that could be anywhere from 3 to 7 knots. A 10 knot wind can be anywhere from 8 to 12. So, and then ones, like we said, the wind's directions are always from. So the wind is blowing this way. So it's from the southeast at 10 knots. Temperature is the top number. Dew point is the bottom. And then the cloud cover, if it's solid, that's overcast. If it's half, that's scattered. If it's 3/4, it's broken. And then if it's got a circle, it's clear skies. And then that one little quarter there is few. So there's few clouds in that at that location. So that's a little bit stuff you need to know when you're looking at these surface charts. I got this overlaid on radar so we can see where the weather is. We can see where overcast. There's 20 knot winds right there, 91 degrees. There's a 70, 72. So you could probably say there's some sort of front right there because of that. This is the warm. It looks like a warm sector. It's probably a front, just by the guess of this thing. And then low pressure is probably to the north. Looking at wind blowing this way, wind blowing that way. It's a wind shift, so we probably got some sort of rotation up to the north. We can pull the station plot, or actually the sea level pressure isobars, and see where our pressure systems are. we'll just do that real quick. I don't want to get too far off course here. So low pressure to the south, low pressure well to the north, looks like a frontal system pushing all the way through the central United States, and then high pressure to the northwest, then that subtropical ridge pushing in on the southeast. All right, so let's get back to the class. Mass, force, and pressure. So mass is the measure of the total amount of atomic matter a sample contains. So if you have a partial of air, how much you got, that volume, you got the mass, and then you got the pressure. We know gravity is constant, so that is the force that's put onto the air parcel and then causes the pressure. So mass is expression of the types of energy that bind it together and its inertia or resistance being moved. Mass is expressed with the symbol M and is measured in grams or kilograms. Okay, Newton's second law of motion, force. Once acted upon by acceleration, mass gains a new property. Force is a push or pull capable of changing the state of motion of the object. Force is written as force equals mass times acceleration, expressed in newtons. Considering weight, this is an expression of force which uses gravity as a source of acceleration. Like we said, gravity is constant, so gravitational force equals mass times times gravity. So back to the force and mass, they're going to be directly proportional if acceleration's held constant. So if you increase the mass, you're going to increase the force. If acceleration is held constant, if you decrease the mass, then the force is going to decrease. So if mass is held constant, you increase acceleration, you're going to increase the force. If mass is held constant, you decrease acceleration, you're going to decrease the force. So there's proportional and inverse proportional again. All right, here's another example. I got a little graph on the bottom that shows you the area. So pressure is a force per unit area. So force divided by area, where force is N and A is area, meters squared. So the key unit of pressure in meteorology is hectopascals. Pressure may be measured in terms of height of the column of mercury in an evacuated tube, expressed in millimeters, or inches of mercury. And the standard atmospheric pressure is 1013.2 millibars, or 29.92 inches of mercury. We'll look at that here in just a minute. So if you look at the force that's applied with mass and area, if you have the larger area on the bottom, 30 newtons, then your pressure is decreased if the area is increased. So your force remains the same. All right, so the pressure will increase. If force is held constant, your area decreases, then your pressure will increase. Now you're taking that same 30 newtons and putting it in a smaller area, so you have a higher pressure on that small area on that surface. So if you look at a high pressure system, let's go back to our weather chart and look at this real quick. Okay, so if we look at this as an example on the surface chart, we can see high pressure, low pressure. So mass over area, for low pressure, you have a lot less mass. You got 1,004 millibars, 1,001 millibar low, 1,013 millibar high. So the pressure is increased because of the mass of the colder air is downward vertical motion over this area. There's the isobar for the high pressure system. There's your high pressure center. So you have a higher pressure because you have a colder, more dense air over this area. Doesn't really matter if you increase that area with that same mass, then you will decrease pressure. But since we have almost a closed isobar, it probably is closed up in that area, but closed isobar right there. This is the pressure over area, mass over area, and that's why we get the higher pressure. Now in the low pressure system, we still have that small area, but now we have upward vertical motion, and then that mass is being removed from the surface. So if we decrease this area with that mass, then we would increase the pressure But with a low pressure system, it's constantly pulling the mass out because it's upward vertical motion. So now we have a low pressure system and a lot less mass. So that's how the mass, the force, pressure over area, all that applies to the surface chart. Like I said, you don't have to do the equations because by the time you do them, it's already done. This low pressure system's already moving out and you already missed it. So, all right, so we're standard atmospheric pressure is 2.992 inches of mercury in an evacuated column, but you got typical atmospheric pressure is basically 14.7 to 1, 14.7 psi per square inch, 14.7 pounds per square inch, a standard atmospheric pressure. So to get an accurate reading, if you were to get an accurate reading across the United States for pressure, these weather charts that we pull up, they kind of just like average lines out, smooth, make everything look smooth. We don't really, that's not really the case, because if you were to actually bring up this, every little station, if I put every station on this thing and we plotted it by hand, we would have a lot of sharp corners going around stations, and it would just look so cluttered that you wouldn't, it just, your forecast would be, it wouldn't help you any. So it kind of just averages it out to make it smooth, make it look pretty. That's all it is. You got to look at the data close, though, to determine, okay, is my low pressure center here in that location? It says 1,001 millibars. We have 1,010 right here, or 1,004. We got 1,004 here. Let's see, that's 104 degrees. I'm sorry. And then we got 1,007 millibars out here. 1,007.6, 1,007.2. So 1,001 millibars is pretty close for this area, because we can come up here. There's 1,004 right there. So there's our 1,004 isobar going around that station. So this is 1,004.1 at this station, then that would be just outside the isobar. So when you're looking at these charts, you need to look at the fine tune on this thing so you can kind of place your fronts, make sure all your data matches up, and then you can verify your center, your low centers, your frontal placement, and all that. So that's pretty much where the importance of these charts. Now, if you threw all the data up here and try to get that computer to analyze all that, like I said, it'd be too cluttered. You'd never be able to see it. All right, so temperature. Temperature is a measurement of the amount of kinetic energy in the molecules of a substance. So the faster the molecules are moving, they bounce off each other and they create heat. So in meteorology, this manifests itself as heat. The standard unit of temperature is Kelvin, 0 degree Kelvin. There's no molecular activity present, and the melting point of water is 273.16 degrees Kelvin. So that pretty much lines up with Celsius. On they have the same intervals. We'll cover that in a second. Temperature is also measured in Celsius. 0 degrees Celsius is the melting point of water, and 100 degrees is the boiling point in a standard atmosphere. So just remember, like, we're saying a standard atmosphere, 2.992 inches of mercury. Well, if you increase that pressure, then your water is going to reach its boiling point faster if you increase the pressure. So decrease the pressure would actually take longer to boil that water. That's why we put radiator caps on cars, is to create that pressure to get it to heat up faster. The faster they get a car to heat up to a normal operating temperature, the less pollution it puts out. So it has a lot to do with atmospheric pressure too. Actually, cars measure manifold atmospheric pressure that will actually, so it can determine how much fuel to put into that system based on the pressure in the manifold. So Celsius intervals are the same as Kelvin. We said that just a minute ago. Since water melts at 273.16 degrees, it boils at 373.16 degrees. 100 degrees difference. So your Celsius scale is 273. That's 0 degrees Celsius to the boiling point, which is 100 degrees Celsius at 373 Kelvin. So those intervals are the same. Basically, just the Kelvin scale takes the Celsius scale all the way down to no molecular activity, and it marks that at 0. And then the final measurement of temperature, of course, is Fahrenheit. If you live in the United States, we use Fahrenheit. Look at our weather charts over here. The surface is in Fahrenheit. Upper levels is in Celsius. So I always keep a conversion chart handy. So when I'm looking at my upper air charts, I can see what the temperatures are. It really doesn't matter to me too much on that, because when I get into the upper air charts, I'm looking for major shortwave troughs, long wave troughs, and then I'm looking for temperature advection. So I don't care if it's 35 degrees Celsius or minus 35 degrees Celsius or minus 5 or minus 10. It really doesn't matter. It's like what's going on in that area for the most part. Is it cold air advection, warm air advection, or no advection, temperature advection? That's what's going to determine, okay, what's happening to the low pressure system on the surface. If I have warm air advection, low pressure system is likely intensifying. So it's actually deepening. So that's pretty much what I'm looking for in an upper air chart. So let's go look at an upper air chart real quick and see what I'm talking about. I'm going to try to do this course as thorough as we can, so it's not just reading words off a screen and then not applying anything. So let's go look at the charts again. All right, I'm going to erase this. We're going to go up to 500 millibar. That's typically a spot to start where to find major short waves that are going to be a significant impact on the atmosphere, on that weather system. 500 millibars is mid-level, mid-upper level, so that's going to be the place to start. That's where vorticity matters most. Actually gives you a better answer of what's happening in that system. So let's go to let me get a pressure reading up here. And then we can then we'll throw the isotherms. Actually, I'll throw some station plots on here just so you can see. This is you can see that upper level low to the north. Pretty zonal flow across the United States. So, but this trough is the support for that surface low. So we do have a significant low pressure system to the north. In the upper levels, based on that surface low. Now let's go, let's throw the isotherms on here. I'm going to throw Celsius. So we can see the thermal advection if there's any. Really not much going on there. So this is kind of a poor example. Let's go, one more thing. We'll put some station plots on here just because. And then we'll go back and get rid of this and pull up. Maybe we'll drop down to the 700. Well, that'll be right around 10,000 feet, just below 10,000 feet, and then see what we got there. So we do have moisture. All these black dots are significant moisture. So you got a dew point depression. We'll go over that later. Of 5 or less. So I don't really see any significant advection right here. So I'm going to get rid of this. Let's go to the 700. See what kind of contours we have. So another thing to remember on the surface, those are isobars, lines of equal pressure. These are lines of equal height. So there are contours in the upper levels. So you can see we got a tight contour gradient here, but so we got a significant low in the upper levels. But what's going on with the thermal advection? That's what we want to see, and it's really not much. Let me get just not seeing the thermal advection. We do have where the isotherms cross the contours. There's very weak thermal advection. So this low is pretty much a mature low. It's starting to fill. This thing just pretty much dying out. So we don't. That's why we're not showing a lot of thermal advection in the upper levels. So that low is kind of probably just going to push to the east and just push to the northeast and more north and just go up into Canada and die out. So pretty much what's happening there. Probably still have that surface front, probably a weak front. There's really not a whole lot of upper level support. Now we got a warm core over New Mexico. Western Texas, if you look at the surface, we have that low pressure system, so that warm air is shooting all the way up into the upper levels. So we got, you know, higher heights, and that low pressure system is pretty much drying out everything right there and creating that heat wave in Oklahoma and Texas. Trough's pretty deep on the 850. That trough is dropping down right there where that surface low was over Texas, Oklahoma, that heat low. So now we do have a little bit of thermal advection at 850 millibars right behind that trough. So if you wanted to, you could almost put an upper front right there. Let me throw the station radio sound data on here. We can get we can see a little bit of our wind kind of shifting a little bit. There's a major shift right here. So we can see those temperatures be 26, 25. Not a real big temperature difference. 17 and 15 on the dew points. Dew point depressions, actually, that's how far apart the temperature and the temperature dew points are. Now, once you get 5 or below, that's where it colors it in. You can see your significant moisture. So, pretty deep trough, a little bit of thermal advection. Here's where I'm talking about, you know, like a major short wave. That would be that low pressure with that thermal advection right around that low. That would be significant support at 850 millibars for that surface low. So once you get in the upper levels, you can see that, you know, it's getting pretty weak. So it is a mature low. All right, let's get back to it. Okay, so temperature gradient. Now, it's the rate of change of temperature per unit distance, perpendicular to the isotherms, like we said, where we had that thermal advection. We'll go back here in a minute and look at that again. Horizontal temperature gradient can be found on any upper air chart, and then vertical temperature gradient can be found on a SCU-T chart by subtracting the lower temperature from the upper temperature, and that will give you your lapse rate. The standard atmospheric lapse rate is 6.5 degrees Celsius per kilometer. So every kilometer, if the temperature changes, so we know in our atmosphere it gets colder as you go up. So if temperature drops 6.5 degrees Celsius in 1,000 meters, 1 kilometer, you're at a standard decrease. That's just normal. So if you start decreasing more than that, you get a steeper slope on that decrease, a higher lapse rate, then you can get into colder air, a lot more dense colder air in the upper levels, and that creates a little bit more unstable environment. Now, depending on what that lapse rate is, if you hit 7, 8, that is a pretty significant difference. Even just that half degree to 1.5 degrees, that's a pretty significant difference to give you an unstable environment that can cause significant weather. So let's go back to the chart real quick and we'll look at our thermal gradient just to give you a picture of that. So if we look at this one, right here's a tight thermal gradient. So if we look at that, where these isotherms are crossing the isobars, the closer together they are, the tighter the thermal gradient. The further apart they are, the weaker the thermal gradient. I may have a picture on the next slide. So, but this is real time right now. This is what actual pressure systems over the United States. So if you look at that thermal gradient, that's what I say when you look at these charts, you see how tight that thermal packing is, and then how strong these winds are, like this contour gradient with the thermal gradient. So right here we're getting significant weather because both of these are tight. So right here is a pretty tight thermal gradient. So what do you need? Moisture, instability, and lift to create a thunderstorm. So we pretty much have all that in this area over the Great Lakes region. Alright, so horizontal temperature gradient. Here's an example on a chart. We got a strong thermal gradient. See the arrows where the isotherms cross the contours. And then a weak thermal gradient where they're crossing those contours, but they're really far apart. So you have really weak thermal advection in that area. You have strong thermal advection in this area. So that's the difference between horizontal temperature gradient. So vertical temperature gradient, you got to go to a SCOT. I don't have one pulled up just a second. But you subtract the upper number from the lower number from the upper number, and that will give you your thermal gradient in the vertical. Okay, so here's an example of that. So, like I said, in our atmosphere, temperature decreases with height. So we're in an unstable atmosphere. Cold over warm is unstable. So cold air wants to sink, warm air wants to rise. So it's a constant changing atmosphere. So we live in an unstable environment. That's why in the troposphere, the layer of the atmosphere we live in gives us most of the weather. So now, if you look above this up here, from 2 kilometers goes up, temperature starts to increase with height. That is a stable environment. So now that is an inversion. It's called an inversion. Then that's basically capping this atmosphere. So any weather that happens down here, it's going to go up to that point, and it can't push that out of the way. So it's just going to cap this any significant weather to these lower levels. Then when you have temperature, now it's kind of a poor example. But it's just to give you a visual. The line straight up, that is no change in temperature with height. So that's isothermal. Pretty much right between the transition between each layer of the atmosphere is pretty much isothermal. So you have the troposphere, and then where the temperature doesn't change, and then you'll have a temperature that will increase with height. So if you took that isothermal, put it over here, you want no change, and then you want an increase in height, you could call that the troposphere, tropopause, and then the stratosphere. So stratosphere is stable, tropopause is unstable when you have that transition point in between. That's isothermal. All right, so 500 millibars, cold air, you have lower heights. So the 500 millibar height, say, will be 540 decameters. That's a lot lower with cold air. If you have a standard atmosphere, it'll put it at 557. Now these numbers aren't 100% standard, but it's like this is just giving you an example of where your 500 millibar constant pressure, constant height chart will put that contour. Is on a cold air, it's going to be lower. Standard air, it's going to be in the middle, and warmer air, it's going to be higher. So like we said, with that low pressure system over Texas, that heat low, we got that warm core system all the way up into the upper levels. Then now your 500 millibar height is going to be a lot higher. So it's a 500 millibar pressure, constant pressure. So the 500 millibar is going to be in a higher heights with warm air, lower heights with cold air. Cold air is more dense. It's a thinner atmosphere. It's pressing down. Now, not really a contradiction on that, but like thing that fights against it, when you do compress air, it heats. So now when you take a high pressure system moving out of the polar region, you bring it south and you push it down on the surface, you're compressing that air, and now it starts to warm. Now that whole air mass is starting to modify.